Let's start it. Myself, Anil Sharma. I'm from Impulse Technology, Delhi. We are based in Delhi, Gurgaon, and I would like to introduce about our company, this Impulse Technology, which is representing several nanoelectronics, semiconductors, optoelectronics, simulation software, as well as some equipment for semiconductor device application. So we'll discuss about Fluxim SETFOS, what this company do, and how these kind of innovative tool will be helpful to boost your research. So let's start it about our parent company. So this Fluxim, which you can see here, it is a Switzerland-based company, Swiss company, which provide the simulation software as well as hardware. Software and hardware, both for experimental setup and simulation software for R&D on OLED display lighting, solar cells to academic institute worldwide as well as the industries all over the world. In India, Impulse Technology is the only distributor which provide these kind of simulation tool. Today, we will discuss about Fluxim product. It is a company name only. If we talk about the product, that is called SETFOS and LAOS. This SETFOS, which you can see, and LAOS, these are two simulation software that will virtually help you to simulate solar cells, different kind of solar cells, as you already seen in the brochures, and LEDs application. Perovskite, tandem, thin film, quantum dot, nanoparticle effects, and some organic solar cells as well, including the light absorbing application and light emitting device application for two-terminal optoelectronics domain, ion recombination, and charge transport domain. These two softwares are there that will help you in this kind of domains. So we'll go in the detail and how it can be simulated, the solar cells and LED, that will also be demonstrated. So keep patience. I'm going to start. If anybody have any questions, you can type in the chat box also, so that I can look into after this webinar. Then we'll discuss about your question and answers. Apart from software, there are equipment is there that you can see. PIOS, Philos, Litos light. These are all equipment for the characterization or measurement of current voltage characteristics and ELPL measurements. So PIOS is basically for electrical characterization, electrical measurement. Philos is for ELPL measurement, and Litos is also for OLED emission measurement. And this is for stability, Litos light, stability, degradation on different channels, 16 channel, 32 channel, or 64-bit channel simulations. So simulation software as well as equipment can also be integrated to each other, so that you can validate your research with the experimental one and simulations one. That's why, as you can see in the bottom of the page, SETFOS, LAOS, PIOS, Philos, Litos light, these are all softwares. First one is called software, and last one is called equipment for the characterizations. So we do provide all the things, all the complete setups. Today we will discuss about only SETFOS, because it is only 1-2 hours time where only one product will be discussed today. So if we talk about the SETFOS, that is basically a semiconducting thin film optics simulation software. It is a complete name. Thin film optics, optical simulation of semiconducting materials. It is basically designed for organic and perovskite based solar cell, including emitting devices. So light absorbing and emitting. It is very fast in terms of calculations. In terms of simulation, it will get it your job within 5-10 minutes. The algorithm which is defined in the background, that is very fast while running the calculations. So it is very powerful and CPU efficient multi-thread for design and development, modeling, simulation of novel optoelectronics, thin film based device applications. It is used to study, to do the research and optimize your parameter based on different solar cells and LED parameters. So I will show you in the live demo how you can optimize different parameter of your solar cells and LEDs. So this SETFOS is very powerful tool to calculate optical property, electrical property, and emissive property, and simultaneously electro-optical and electrical emissive property simultaneously at a time. So let's discuss about the application part, where the SETFOS is majorly useful for organic related applications, silicon based solar cells, thin film structures, perovskite, tandem structure where multiple layers are there, multi junction, two terminal junctions, three terminal junctions, four terminal junctions, multi terminal junction transfer matrix theory is included in that to calculate the depth diffusion equations. So heterojunction solar cells, thin film solar cell, dye-sensitized solar cells, organic solar cells, photodetectors, quantum dots, LED application, including the perovskite, white LEDs, TADF LEDs, polymer LEDs, polymer solar cell, and high fluorescence. This is a major application where the software is dedicatedly designed for such application. Many of the participants also registered for nanomaterial applications. So we also have the solution, those who want to work on nanomaterials. I will show you end of the slide. So let's discuss in the detail about this SETFOS. This SETFOS is divided into 4 modules. There are 4 modules are there, because some of them are working on only solar cell, some of them are working on only LED, and some of them may be working on solar cell and LED both. That's why the software is divided in 4 modules. If we talk about the first module, that is called absorption. It is basically for light absorbing module, where it will judge, it will get how much the light will get absorbed by particular material or particular device. That's why this absorption module will be required, where we can define the spectrum, air mass 1.5, air mass 0, global spectrum, direct spectrum, or particular location and time specific spectrum. That can be followed by using this absorption module, and light will be observed by this absorption, and it will predict the optical analysis. So for that optical analysis, this absorption module is required. If you want to perform optical as well as electrical calculations, some IV measurement, band gap, homolungo, charge transport, ion transport, recombinations, then depth diffusion is the second module, where for electrical calculations, this depth diffusion module will be required. If you want to do the optical and electrical both, then both the module are required of absorption and depth diffusion. If you want to work on only electrical calculation, depth diffusion is required. Only optical calculation, absorption module is required. If you want to go beyond that depth diffusion or transfer matrix, you want to include the quantum dot effect, some texturing effects, some ray tracing, Fourier analysis, wire fringents, some ray tracing study, and different interface quantum dot related property, then this advanced optics module is required for higher advanced research. And if you are working on emission module, then this emission module will be required. So either you can plan for 1 module only, or you can plan 2 module, 3 module, dependent on the need, your requirement, your area of interest. So this software is divided into the module. Now let me discuss about each module, what are the major function of the module is. If we talk about electrical property calculation module, that is called depth diffusion. This basically will calculate the electrical property of solar cell and LED. It is a combined module that will work on LED as well as solar cell for electrical analysis, for depth diffusion calculation, for IV calculation, recombination, charge transport, ion transport, power conversion efficiency, quantum efficiency, DC simulation, AC simulation, transient simulation, impedance measurement, impedance spectroscopy analysis. For that purpose, this depth diffusion module is required. It contains state-of-art mobility model, constant mobility model, and organic mobility model. So electron and hole mobility can be defined as a parameter while modeling the structure. Poole Frenkel, field dependent, time dependent, temperature dependent, and state of art other mobility model are there, like extended Gaussian type disorder and correlated type disordered mobility models, including the conductive doping, charge trapping. You can apply the voltage rising on the contact, and you can calculate the electrical property by using this depth diffusion module, including the excitons, generation, quenching, diffusions, anion, cations, and including the circuits. Let's suppose as an example, you want to define such type of structure where there is a top electrode is there, then ETL layer, HTL layer, or semiconducting layer, perovskite layer are there, and back electrode. So that kind of structure you can define, and you can apply some voltage rising, and you can see different by varying the thickness, by varying the voltage, by changing the wavelength, or any parameter, work functions. So how the device parameters, device output are changing with respect to the input, and then you can optimize your structure based on the particular requirements. And you can also attach the electrical circuit parameter RLC component with your devices. We talk about the other model. All the efficiency are based on the model, physical models. So in terms of physical model, it contains all conductive models, charge transport models, traps model that can capture the electron and hold trap density models are there, impact ionization models are there, SRH recombinations are there, trap recombinations are there, auger recombination models are there, polarity of charge transport layers models are there to improve the charge injections. So from simulation to the experimental validation can also be integrated with the equipment, so that the result whatever coming with the simulation, that will also be matched with the experimental results. So ion transport model are there, anion and cations, electronic charge transport, hysteresis models are there on different particular ramp rate, pre-rising temperature, and different other transient related parameters like voltage transient, and other transient parameters can be defined like implicit Euler, Runge-Kutta, Euler mode point. These are the some transient effect study can also be done. So steady state, DC, AC, transients, impedance, and conductance will also be there. So you can see this is one current voltage characteristics by changing the thickness from 50 nanometer to 250 nanometers. So multiple graphs you can see. One is plotted at 50 nanometer, second one is 100 nanometer, 150 nanometer, 250 nanometer. Simultaneously, you can also sweep any parameter, either at a voltage. You can set minimum range, maximum range, and how many iterations from minimum to maximum you want to perform. Software will do this all the thing on single click, and it will plot you the results in a HTML or single file where all result will be plotted. I will show you in the live demo how it will be done, so that it will clear more all your doubts. Not only a charge transport is there, interface model is also there. There are two layers are there. One may be a P dot or PSS or HETL or perovskite layer interface are there. So interface related theoretical parameter is also included. So charge generation, recombination at the interface of two layer heterostructure for solar cell and LED to connect the multiple terminals. So 2 terminal, 3 terminal, 4 terminal, all things will be possible, including the electrical modeling of solar cell, recombination, organic, hybrid multi-junction, tandem perovskite, hopping between different states at the interface, injection layer modeling, charge generation, HUMO-LUMO modeling are there. From you can define the HUMO value, LUMO value, and electrical interface will be there. This is all about the depth diffusion model. So effective medium approximation, Bregman, Maxwell, Garnett, porosity, Cauchy, Shelmier, Lawrence, Tau, Root. These models are also there for effective medium and some surface texturing, surface scattering analysis. I will talk about the absorption module that will required only for a solar cell application. This absorption module will use basically a transfer matrix for fast calculation in the solar cell. It can maximize the light absorptions. You can optimize the layer thickness, you can optimize the layer material and match the short circuit current of different with respect to your solar cells. You can also compute the absorption of each specific layer. Whatever the layer you are using for your solar cell, then you can find that which layer are getting more absorbed light by using this absorption module, including the total absorption for the whole devices. So material based absorption and total device absorption can be calculated. Reflectance, transmittance, absorption spectra, angular dependence, polarizations, and light spectrum with AM0, light spectrum with AM1.5, global spectrum, direct spectrum, or even location specific spectrum can also be defined. Let's suppose you are sitting in Bombay. On Bombay, where is particular location, there may be some different sun angle, maybe some different light radiation will be there. So that light can intensity can be absorbed according to the specific location, specific geographical time. Specific, let's suppose in the morning there may be different intensity, in the daytime there may be different intensity, in the evening time may be different intensity. So based on that, some realistic models are there so that you can see at what particular location how much light will get absorbed by the device. Mixed coherent, incoherent, maximum power point, optical and electrical, both simulation can be performed. This is one experimental paper where the DOI number is also given, where we have calculated around 95% accuracy theoretically in terms of experimental and simulations. So this is one paper which is published by even IIT BHU, and they found this experimental and simulation why using the SETFOS are more reliable, and around 95, 98, 92% accuracy can be predicted based on virtual simulations. So experimental and simulation, both things can be studied, and you can see how this tool will be better. If we talk about for the emitting devices, LED related application, where emitter can be set, you can set in between the electrode, there may be some single emitter layer or multiple emitter layers. So you can select which layer as an emitter, you can define it. There is an option called to define the emitter layer. Either you can define single emitter layer or you can define multiple emitter layer. You can do the extraction of emission zone, source spectrum, emitted power, radiated powers, top and bottom emissive property, how much the radiance will be there, electroluminance, photoluminance, dipole emission models are there, user-defined dipole distribution models are there, coherent, incoherent, roughness parameter, dipole arbitrary orientations, physical quantity are there, emission color characteristics, CIE, color diagram, RGB, you can plot it, applied current density, reflectance, transmittance, absorption spectra, figure of merit, angular dependence, polarization, coherent, thin film, radiance, luminance, luminous efficiency, current efficiency, dipole, emission spectrum, optical modes, angular radiation characteristics of LEDs, and you can optimize different layer thickness based on particular emission colors, emission spectrum, normalized emission, white emission, S polarized, P polarized, unpolarized, SP polarized. So these are different emission spectrum. You can plot it. You can see these are different color plot that is calculated by using our SETFOS tools. If we talk about the module, next module that is called advanced optics. It is module is basically required for non-flat structures. Let's suppose you want to simulate a solar cell where the structure is not flat. There is some textured surface is there to get more light absorbed. So that non-flat layer, micro size or nano size feature that can scatter the light outside the specular directions in reflection and transmissions. So this interface can be external interface or it could be an internal within the layer stack. So multiple layer stack you can define. You can import the AFM, or BHDF experimental data to create the non-flat textured surface. You can simulate the micro lenses, texturing by the ray tracing, geometrical wave optics, scattering by the particle Gaussian monodispersions, or Lambatian, Pong, Gaussian, Fourier, 3D ray tracing, root mean square, RMS setting, roughness parameters you can define to calculate the H for top and bottom interface. I can see this is one layer stack. In the between the glass and high index layer, there is textured surface is included. So AFM textured surface is included, and accordingly you can calculate the texturing analysis, scattering, ray tracing analysis by using this advanced optics module. So whatever the module is convenient for your research, that you can pick for your needs. We have 1 year, 3 year, 5 year, 10-year license policy. Since it is a commercial license version tool, so different options are there. If we talk about the advantage of the software, there is a very sophisticated graphical user interface. You have no need to write the code. You have no need to learn any language. It is fully designed software with a sophisticated user interface. You have to think about the physics, and whatever the physics parameters are there, just include in the tool. It could be optical parameter, it could be electrical parameter, voicing parameter. You can visualize, you can define as an input. Software will do the calculation based on theoretical analysis, and it will predict you the output in a PPT format, in a HTML format. So very sophisticated user interface, easy to learn. It is just plug and play. Already the developer have worked a lot to create a easy to use interface. There is ion transport models are there, anion, cation with hysteresis effect, Windows, Linux as well as Mac OS is also supported. Default parameters is great convergence. Whatever the parameter defined in the background, it will converge quickly. So you will not find a lot of convergence issue. Convergence issues are minimized in the tool. Scattering interface are there to define the roughness parameter. EFM, BHDF data. You can also import the experimental data. It supports DC simulation, AC simulation, impedance analysis, which cannot be done by any tool. Transient simulation cannot be done. Ion transport will not be possible in any other software. Convergence issue may come in other tool, and some PPT will be presented automatically. Unlimited number of layers it will support. It is not restricted on 5 layer, 6 layer, or 7 layer. Up to n number of layers you can design the structures. So layer stack 15, 20, 30, 40. It is not restricted like open source tool are available. It is a light can be absorbed in particular material or whole devices. In a single click, you can visualize, you can do the calculation on different value of your simulation. Like let's suppose from 100 nanometer thickness to 200 nanometer thickness, you want to see your plot. Then single sweeping and optimizations are there where you will get your plot very quickly. Updates comes regularly. Whatever new research are going in the industry, that software updated keep regularly within a 6 month or within every year major update come. Technical support will also be provided so that you will get it more very you will not find any problem while using the tool. It will also help Poole for quantum dot, nanoparticle, texturing, electrical, optical, layer, sweeping, optimization, emission related property that cannot be done in other application where it can also do the emission CI color diagram, electroluminance, photoluminance. I will show you how it will be done. So this is all about some theoretical model is also there, temperature, trap, ion models like that. If we talk about apart from SETFOS, there is another tool that is called LAOS. It is basically for large area semiconducting devices. If you want to work on large area solar cell, where connected cells, module simulation, then there is another tool. It is different from SETFOS. SETFOS is finished, presentation is finished. I want to discuss about other product that we have. Then we'll go for the live demo. So this LAOS is basically for large area organic semiconductor device simulation. So it is based on 2D plus 1D. one-dimensional. SETFOS was one-dimensional, but this is 1D plus 2D FEM-based simulation for large area solar cell and LED to perform the electrical, thermal, and optical calculations. Whatever the losses are there in your solar cell and LED, if you are getting a low efficiency, then what could be the reason behind that? That losses study can be performed by using this LAO softwares. So electrical loss, ohmic loss, heat loss, geometrical loss. For that purpose, there is electrical module is there for electrical loss analysis. For heat temperature loss, there is thermal module are there. For optical study, this optical module are there. Similarly, like SETFOS is divided in 4 modules, and this LAOS is divided in 3 modules. Whatever module for convenient, that can be planned according to your needs. So this module will basically work on large area devices, not for small cells. It work on large area solar cell as well as module simulations. Now, if we talk about, I have discussed about the top product, SETFOS, LAOS, and these are equipment similarly for characterizations. If many of the participants registered for material simulation, nanomaterial related application, for those participants, I want to tell you that we have a nano academic technology, which is one of our partner, which provides the atomistics material and device simulation tool based on DFT plus NEGF, quantum transport calculation for crystal simulation, molecule simulation, device simulation, interface, quantum technology, spin qubit device simulation. So these are all our products that I wanted to share with you. So this is just brief idea about the presentation, what the software belongs to our company, and this is my contact information. You can also take the screenshot or photo of this picture so that whenever you have any problem, you can drop me the email or you can contact us so that we can help you how this kind of innovative tool will help you to boost your research. So participant can also type your query in the chat box. So after the demo, after 1 hour or so, I will look into your questions and then will unmute your mic, unmute my from my side your mic also, so that you can also chat with me directly. So thank you very much for giving your time. Now I want to show the live demo on the software, so that you will get to know about the software capabilities. So I would like to open the software that is called SETFOS 5.4. I would like to right click and run as an administrator. Now it is opening the graphical user interface of this SETFOS. Now the graphical user interface is open. Recently, SETFOS 5.4 version is released, where you can see whatever the new features are developed that can be visualized on top of the screen. So this is called current source boundary condition for electrical simulation. This feature is developed recently, where it is showing with a screenshot. Similarly, once you click on the next page, then you can find the next feature which is developed about the impact ionization model in the tool. If you will click on the next page, AC responsivity for the photodetector simulation, that is also developed. For you can now sweep different column for emission analysis. If you want, there is more robust diffusion solver with increased numerical precisions to improve the stability with the low charge carrier density, and many more features are under development. So you can see these are some new tutorials also got enabled for AC quantum efficiency and C-Lib simulations. And I want to close this new feature window. Would like to show you the main window. This is a main graphical user interface which you can look like here. Now, if you want to see here, for the beginner, there is a help option is there. In the help option, you can find manual and tutorial. Manual basically, if you want to know the background physics, background models, equation, on what basis the software is developed, and you can click on the manual page. Once you click on it, in the manual page, the background theory is given. Now you can see here, this is background theoretical explanation that is given in the manual page. You can go down and find all the equations, all the models, all the physics parameter that is well given in the backgrounds. So manual can be look into that whenever you are going to work on any simulation paper. That time the theory part you can look into from the manual page. So this is all parameters, models, equations, quantity as an input, syntax of the input quantity, that is all given. So I cannot explain everything about the manual within short period of time. So this is just for your knowledge. So in the help option, there is not only a manual page, there is a tutorial page is also there. Once you will go to the tutorial, then you will find the tutorial that how step by step you can use the tool. So once you see here, there is a bibliography option will be there where you can see the detailed content, how you can start your first light emitting diode, how you can first white OLED, or how you can simulate your first solar cell. So once you click on that, you can reach on that particular page and you can follow this tutorial. You can see here, this is tutorial with proper screenshot so that you can create different stack very quickly with proper explanation is given. How you can vary different thickness of the material. So tutorial and manual, this is just for beginner, how we will start quickly on the tool so that you will not find any difficulty while creating any different or complex structures. Apart from that tutorial and manual, there is a videos is also available, and apart from that example is also available with a lot of variations parameters. So I want to start from scratch instead of opening the existing project. I want to start from beginning. To start from beginning, there is a file option is there where you can click on the new options. So I will click on new. Initially, I want to take a small solar cell, then we'll go for LED applications. So I click on file and click on new option. By default, there are three layer is created automatically: surrounding, unnamed, and substrate. These are three default layers, which will also reflect in the right side. Right side layer structure in this green layer and surrounding, incoherent, and substrate in the bottom. This will automatically change. There is no need to change in the right side of the structure. Everything will automatically change if we will change from the left side. In the left side, there is surrounding, unnamed, and substrate. Accordingly, you can visualize on the right side with their thickness value is there. So in this particular example, first of all, I will show you how to perform the optical solar cell calculation. Then we'll go for the electrical one. So I have to activate the module. As in the presentation session, I told you there are 4 modules are there in the SETFOS. So for optical calculation, absorption module need to be enabled. So I will click on this absorption part and the module need to be enabled. You can see this absorption setting has been enabled. Once I click on this sign button, this sun button, I click on it and this absorption setting module is enabled. Now once I click, you can see here. Now as you know, the solar cell is surrounded by the air. Therefore, we will remove the top layer name. We will define air because solar cell is already surrounded by the air. So air is there on the top side and air will be there on the bottom sides. So I will rename it layer and I will define it. So top and bottom layer is called air. Now in between this unnamed layer, I have to add multiple layer and will create the layer stack. For creating, I will simply click on this add layer button. So I click on this add layer button. Once I click on that number of time, accordingly that number of layer will be added. So I'm clicking it and it is adding, that you can see here. Right side, it is automatically reflecting. So as much as I will click on this add layer button plus sign, it will add accordingly. So there's maybe some software have limitation, only 6 layer, 7 layer. But here you can see there are so many layers can be created. You should have a complex structure. The complex structure can be created by you. If you want to delete particular layer, you can delete that particular layer also. So a lot of your time can be shaped like that. So it is default, everything is there. Now I want to define my layer stack. So I have added these layer. So I have to rename my layer parameter. So first layer I want to define, that is called as example glass layers. So glass layer thickness is basically unimportant because it will become as an incoherent. So I will treat as an incoherent and transparent. So I have enabled this checkbox. Glass layer will become incoherent and transparent. Now I will want to define the solar cell that will compresses of ITO. So I will define the ITO layer as an electrode layer will be defined in the lateral stage. And then next layer I will define as an example P dot. P dot PSS we can take. And then I will take it the next layer P3HT PCBM as an example. So this is our P3HT PCBM layer, and then I want to define the next layer that is I can assume like aluminum. We will define this layer property nowwards. So once it is defined, then I have to define the thickness of my layer as well. So thickness of this glass layer is unimportant because it is incoherent and transparent. Now the ITU thickness I want to define as example 125 nanometer. If you want to define in micrometer, millimeter, you can see different units are there. According to your need, you can define that particular units. And this P dot layer I want to define as example 50 nanometer. And this P3HT PCBM layer I want to define as 100 nanometer. And finally the aluminum layer that I can define as example 500 nanometers. So this is my layer structure. You can see in the right side, the layer structure is created. Now, I have to add the refractive index of each layers. You can see top air and top bottom air is there. Now I have to define the glass layer refractive index. So you can see there is refractive index tab where real and imaginary part of this refractive index need to be assigned. So I have assigned this refractive index for glass n equal to 1.5, real part, and imaginary part equal to 0. And for this air layer, I can set, you can see, constant refractive index, real part equal to 1 for top and bottom. Both the layer, we can define 1. Now, in the solar cell, as you know, the top and bottom layer that represent the corresponding medium. And that is a transparent. So we can set it as a transparent, the top layer and bottom layer. Defaultly, it is incoherent and it is transparent. The direction of the light incoming in the SETFOS is always arriving from the top. You can also make it inverted as well. If you want to make it inverted, that will also become possible. So light will come from the top. So in this current situation, the incoming direction is from glass layer, glass active layer. So the direction of the reference direction for the calculation of reflectance and transmittance of the thin film structures. Now this glass layer I also treated as incoherent. So the checkbox are activated. Now I will go to this absorption setting. So in the absorption setting, there is a option called single wavelength or sweep wavelength. So if you want to follow the light, so initially I took this structure and would like to calculate the optical property. So I can define my name of the project, solar optical property. Unique name need to be defined. Now I want to run the job. So I will click on this run button. Now simulation is going on and simulation is finished. If you will go on the bottom of the analysis part, result window, there is a layer absorptance option is there. Just a minute. Sorry. We have to assign the refractive index of this ITO, P dot, P3HT, PCBM, and aluminum layer also. So only glass layer and air layer we have defined the refractive index, but not for ITO, P dot, P3HT, PCBM. So we have to define for that refractive index as well. So I will go to this, I select this ITO layer, and here the refractive index for ITO is not constant. It will be dependent on the wavelength. In that case, I will click on this file option, and here there is an option called new and import. If you have a new refractive index file for this ITO, then simply click on this new button and select the desired file. NK file stands for real and imaginary refractive index. EM stands for effective medium approximation roughness parameter, and analytical dispersion. AD file for analytical dispersion, effective medium approximation roughness parameter, and refractive index, real and imaginary part, NK file. So you can define your new optical refractive index parameter. If you have own refractive index of the material, any material, you can also define your own parameter by defining the wavelength and real and imaginary parts. So I click on this add button. Let's suppose you want to add the new refractive index. You can click on this wavelength value, click on N value, and click on K value, real part, imaginary part. Again, click on this add button, define the new wavelength value and new value of real part, new value of imaginary part. And similarly, you can click again and you can click multiple times and it will add the number of wavelength and real imaginary part. It will also generate in the script. You can see this is a script here. If you will copy and paste, that will also become changeable. Like if you will change the value here, you can also write the script in this particular editor, and it will reflect in the graphical user interface. That you can see the graphical user interface, the refractive index is added. So in this way, if you want to create your own refractive index, you can add that as well. Or you can also import from open source library. If you talk about our library, then you can see there is import button is there. Once you click on this import button, there is a library of the refractive index that present in our database. So ITO, this is all about refractive index database. Mostly all material are NK file, .nk extension is there that represent the refractive index. These are all database that exist inside our software. So mostly all material will be presented available. If you talk about the ITO, I will click on there and find out where the ITO.nk file is present. You can see there is one ITO.nk, multiple variation NK file is also present. I want to open it. You can see it is now loaded. This is loaded here in the screen, and black one is called imaginary, black one is called real part, red one is called imaginary part with respect to wavelength for this ITU. Similarly, I click on this P dot and click on file option, constant file option, and import the material from my library. So I will click there and find out my P dot layer NK file. So let's suppose this is P dot optical refractive index that I have assigned from my library. Similarly, I click on this P3HTPCM. If you have your own refractive index or any other material, you can also upload it. Now I click on P3HTPCBM, click on import button and find out the P3HTPCBM refractive index. As an example, I am taking it. Material could be a different one as also. And now it is loaded. So these are all refractive index for 3 different layers. And similarly for aluminum one, I want to import from my library. So I want to load it here. Now all refractive index are loaded. Now I want to run the calculations. Now simulation is started. Layer absorptance has been changed. So you can see these are different layers. Red color layer is unipolar. This green layer is called glass layer. ITO layer is the called green one layer. And this pink one is called P dot layer. P3HT PCBM is this layer and this is uniform layer. So these are multiple layer and reflectance, layer absorptance you can find accordingly. If you can hide all the layer, whatever the layer you want to see the output, it will plot that output of particular layers. So whatever the layer is convenient, that is getting more light absorb, you can enable it. Like I want to hide some layer, only you have a requirement of P3HT PCBM. So this is a P3HT PCBM layer absorptance from this particular wavelength to this particular wavelength. You can also change the wavelength of the light. So wavelength of the light is given imported in this particular absorption setting where the spectrum is taken. You can see the 380 nanometer wavelength to 780 nanometer wavelength, which is varying, which is changing from 380 to 780, and illumination spectrum file is loaded from the library. This is a sun spectrum, AM0, AM1.5 or other spectrums. So it is already available in the library. If you want to use different other spectrum, you can see that is a white spectrum, location specific spectrum. As I told you, particularly whatever the location you are setting on geographically, that particular latitude, longitude, date, time, angle, cloud, weather condition, how much light will get absorbed in the weather, maybe very little light. So that intensity of the light can also be predicted based on this theoretical analysis. Now you can see this blue one is called the light which you want to fall, and this red one is the light, the total light of this AM0 or maybe AM1.5 spectrum. So I will click on this result window. Now, if you want to see the absorption profile, this is an absorption profile in this P3HT PCBM layer. So air, glass, ITO, P dot, P3HT PCBM, aluminum, and this one. So P3HT PCBM is more absorbing material. Now, if you want to sweep the wavelength, let's suppose there is an option called sweeping. If you want to enable the sweeping, you can click on this sweep, and if you want to sweep the thickness of this particular layer, P3HT PCBM thickness. So I have selected, and let's suppose you want to thickness from 80 or 50 to 200. Let's suppose 50 nanometer to 150 nanometer. You want to switch as an example with increment of 10 steps. So 50, 60, 70, 80, 90, 100, 101. At 10 each step, it will run the calculations. I will right click and perform it, the simulation. And now you can see the simulation is done. Now you can see the with changing of thickness of P3HT PCBM from 50 nanometer to 150 nanometer. You can see here the thickness which I am changing here, absorptance is changing. At 50 nanometer, what could be the absorptance? At 60 nanometer, 70, 80, 90, 100, 110, 120, 130, up to 150 with wavelength. Similarly, all the characteristics, whatever, if you want to see this one also, from 50 to 150, P3HT PCBM thickness variations. So any parameter, as an example, I took the thickness. But if you want to sweep the voltage, wavelength, temperature, HOMO-LUMO value, dielectric constant, or anything, work functions, whatever you know, that value can be swept so that you can optimize your structures. So this is all about the optical calculations. If we talk about the electrical calculations, for that electrical calculation, and you can also check the photocurrent. I wanted to tell you this is a photocurrent from 50 nanometer to 150 nanometer for P3HT PCBM layer. This pink layer that you can see P3HT PCBM it belongs to, and it is showing the photocurrent value. If you want to see the stack contribution in the photocurrent, that you can also visualize, and some reflectance you want to see, transmittance you want to study. This is transmittance, and how the transmittance curve will plot, that can also be studied. Now this is all about optical calculations. If you want to perform the electrical simulation, then I will also perform the electrical simulations. So let's see how we'll perform the electronic solar cell simulations. Now for that, what I will do, I will activate the module first, because for electrical calculation, module need to be enabled. So I will click on this drip diffusion module. It is now enabled. That you can see, it is enabled by clicking on this battery side. The drip diffusion module is enabled. Now when I set the P3HT PCBM layer, these all layer, P dot, P3HT PCBM layer, I have to set this P3HT PCBM as a semiconducting material, because I want to define the electrical calculations. So I will set as a semiconducting. Once I will enable the semiconducting, this tab will become enabled. If I disable it, there is no semiconducting tab. If I enable it, semiconducting tab is enabled. In this semiconducting tab, we have to set the electrode. So let's suppose you want to set the electrode. So this is called ITO. If you want to use ITO as electrode, you can see there is option checkbox called electrode checkbox. Bottom one, there is checkbox. This one, electrode checkbox. And this is P3HT PCBM. Or let's suppose I want to check not this ITO. As an example, I am taking it this P dot as electrode. So we can take it like single layer semiconducting, and this layer is become active electrode layer. So I have to define the work function of the electrode as well. So this top P dot electrode, I have to define the work function. So you can see there is a electrode type, ohmic type or thermionic type. Ohmic type or thermionic type, two type of electrode can be defined. Work function, hole density, electron density, you need to define it. For the time being, I want to hide this layer structure so that I can see the background behind the scene. So this is work function. I can define 4.0 work function of this P dot. Similarly, the bottom aluminum, let's suppose 4.8 something for this P dot layer, and for this aluminum 4.0, I want to define the work functions. We can also sweep the work function if we want. Now to calculate the electrical property calculation, current voltage characteristics, there is a depth diffusion module where you can see there is a steady state calculation, transient simulation, AC impedance simulation, IMPS, IMBS, intensity modulated photocurrent, photovoltage, spectroscopy analysis. For that purpose, these are some type of depth diffusion study you can perform. Now, depth diffusion steady states is defaultly defined. Here you can see the voltage we can apply or current as electrical source on top or the bottom terminal. This is a temperature. We can also set our temperature. This is bipolar device, unipolar device. So both optical and electrical absorption and depth diffusion model will automatically couple to each other. If we talk about this P3HT PCBM layer, there is a semiconducting option is there. Now here, either you have to define the semiconducting property of this P3HT PCBM or you have to import from the library. So there is an option called charge. For the charge transport, there is energy level 5.6 defaultly defined. If you want to edit this value, you can also edit the HOMO value. You can also edit the LUMO value of this P3HT PCBM, which is selected layers. If you want to define not only energy level, you want to set the density of states, you want to define the dielectric constant. So this is dielectric constant can also be defined. If you want to dope particular layers, so this is called acceptor doping. You can define the N-type doping, P-type doping. So you can define the concentration of particular doping. So this is a doping type. So this is acceptor doping. Similarly, if you want to define the donor doping, that need to be enabled. If you will go down, there is a layer for optical generation efficiency and mobility model. Electron mobility need to be defined, hole mobility need to be defined. Either it could be a constant type mobility model or it could be a field dependent type mobility model, temperature dependent type, extended Gaussian type, extended correlated type, field temperature. These are the different type of mobility models. So you can choose that different type of mobility model and define the sigma, tau, gamma, mu e and mu p value according to your convenient. Whatever the option you will enable, it will show accordingly. Similarly, once you will click on the Exciton option, click on the Exciton add button, where you can define the radiative decay rates, non-radiative decay rates, generation efficiency, diffusion constant, saturations, annihilations, Exciton, polaron, quenching, TADF, Exciton, quenching, thermally activated from low energy to high energy, transfer calculations, energy transfer rates that you also need to enable for LED applications. If we will click on this trap option, there is a trap. You can enable the trapping, enable the SRH recombination trap, trap recombinations, single energy level traps. This is single energy traps, exponential density of state traps, and Gaussian density of state traps. These are the different type of traps that is enabled here. So this is a type of trap that is enabled. And if you will go to the next one, let's suppose you want to go to the mobile ions, anion and cations. So once you will activate it, you can assign the anion and cations with a mobility model. So these are all mobility model that can associate with the anions and cations. And you can define their minimum density and maximum density once you enable the particular checkbox. Infinite density from minimum to maximum can be defined. So this is for ion charge transport calculations. For recombination, you can see there is a bulk recombination, Langevin recombination model is there, Agar recombination is there, bimolecular is there, and simplified SRH recombinations. So once you will define the recombination with their parameter need to be enabled, including there is a impact ionization model is there. So once you will enable the impact ionization, there is a China with impact ionization, China with linear, and Thornberg models are there. So their threshold energy need to be defined for the different models. So you can see these are different models that can be enabled for the recombinations. So charge transport, recombinations, trappings, all are there. Initially, I want to import the material library for this P3HT PCBM. So I will click on this import button. There is a inbuilt semiconducting library there in our software database. If I go there, you can see this is called em file .em extension. In this .em extension, there is all electrical material, electrical semiconducting material. So I have to enable the P3HT PCBM, P3HT PCBM electrical material file. So let's suppose P3HT file is there. I can select and open it. Now the all parameter, whatever it is available, that will automatically fill it. If you would like to check the script, there is a script editor is there, which you can visualize your script from here. So this is a script where all defaultly homolumo value is given for this particular material, epsilon dielectric constant, density of state, optical generation, constant electron mobility, hole mobility, it is defined. So this is all things recombination, Langevin recombination that is enabled. Now once it is done, then I will perform this, rename this project optical and electrical, and then we'll run the calculations. Now simulation is started. And simulation is done. If I will click on this device current, it is plotting this device current value. I have to sweep the voltage also. So I will go to there, and in the dip to diffusion calculation, I have to sweep the minimum and maximum voltage rising. So I will go there, and here I will click on add button and sweep the voltage. So I will go there and click on voltage sweeping also. So let's suppose minimum value, I want to sweep from -1 volt to plus value, I want to define 1 volt. So -1 to +1 with the incrementer of 0.1. So you can see here, not only single parameter I want to sweep voltage as well as P3HT PCBM thickness. I can also reverse the each other. Now I want to run it the calculations. Now simulation is running, and you can see here, you can click on this device current, and how from -1 volt to +1 volt the device current will change, or so based on that you can see there is some different Venn diagram is plotted by bearing the thickness of P3HT PCBM and changing the negative biasing to positive biasing. So you can vary not only thickness, this is thickness variation and voltage current variations. Similarly, other characteristics, you can plot the charge, you can plot the charge density, you can plot the recombinations. This is recombination, and you can also see this Langevin recombination that will become higher, and you can see how the voltage variation will affect your device characteristics. This is power density plot. And other spectral analysis like absorptance analysis, layer absorptance. I have taken the random structures. I don't know what is your particular structure type, but once you will have any possibility to procure this tool, then you can also definitely simulate your particular projects. So this is all about the basic idea how you can start from scratch and from single optical calculation to the electrical and optical both calculations. Then there is option called steady states. If you want to steady state to transient, then a transient simulation will be there. For illumination, electrical, that transient electrical property, illumination and temperature. Transient solvers are there and AC impedance are also there. If you want to perform the impedance study, this is for amplitude and frequency impedance study analysis. Now I click on this right side top workspace view where it will open the left example window. Now in this left side, you can find there are a couple of examples are there. I want to open some of the examples so that you will get to know about the complete multiple layer structure view. This is like one full Y-layer solar cells where air, glass, ITO, some different material and interface is also created. This is option add interface. This option will create the interface in between two materials. So this is multiple structure that is inbuilt I have imported. The procedure I already explained, what is the procedure, how it can be done, and some procedure need to be followed to create other complicated or structures. And accordingly, you can find the excitons, hopping between different states interface, trap interface is there, interface recombinations are there, C60 are there, and aluminum ALQ3 are taken on the bottom. If we talk about the voltage is sweeping here also from -1 to +1 with 0.1 increment. Let's run the job for this particular example. Now you can see it is done. It is done. You can see the display key figure. In this display key figure, you can find the BOC value. You can find the GSC value. You can find the fill factor value. You can find the maximum power density in watt, milliwatt, and power conversion efficiency. If you want to plot in the form of graphical, this is a device current from -1 to +1. Current IV characteristics from -1 to +1 without recombination, with recombination, and Langevin recombinations. Three plot will be there. Some of them will be like overlapping to each other. You can see this is a recombination language recombination and without any recombinations. If you want to export your data, simply right click and click on print, or you can save in the form of image part, or you can form in the visible text format, image format. The data can also be get it export. You can see the text format is there. Excel format, you can also take your data to be extracted and click on save it. The data will become export on the plot. You can see this is a data that is exported from the graph. So similarly, all plot, whatever the plot will be there, data can be extracted. Now this is all about the single or multiple layer structures. If we talk about other structure that is given in the library, so I want to show you here. This is one another similar kind of structure that I have shown you. If I will go to the perovskite one, this is one perovskite transients study PL measurement, and this is one multiple perovskite layers, or even this is more complicated where two, you can see here this one ITO, ETL, interface, perovskite, interface, HTL, and silver. And right side visualize the structure. This side you can see the energy level. Let's run the simulation with interfacing of trap density. Voltage interface, trap density interface, it will be there. Now simulation is going on. You can see here how fast the job in terms of simulation. So it will not take much time. Either you have simple normal laptop. So normal laptop will also simulate your device structure quickly. I click on this device current. You can see this is a exact structure, IV characteristics that you wanted to plot. You can see by changing the interface trap density, how the current voltage will change with recombination, without recombination, SRH recombinations, or with the recombination parameter. Four graphs are showing. You can see these are C60 interface bearing parameters, or ETL, HTL layer trap density bearing, how the IV characteristic will vary. Similarly, this is a trap interface density. So how the trap interface characteristics plot are there, you can see like that. Similarly, power density plot, this is a power density output are there. If we talk about other fill factor related, this is fill factor with respect to interface trap density. If you want to increase the trap density, how the fill factor will vary. Similarly, current, power, variation of density, trap density. So similar, any parameter can be vary. As an example, they have taken. This is a band diagram from 0 volt to 1.1 volt, and variation of trap density. And if you want to see a visualized characteristics, this is graphical visualizations. And similarly, if you want to see the electrical field, you want to see the potentials, so you can see all the related output analysis. This is photocurrent value, absorptance value, and other characteristics. Now I have told you about the basic idea of our solar cells. If you want to see more about it, there are some more solar cell quantum dot related option is also there. You can see this is one another structures. For quantum efficiency calculation, I click on it. You can see there is some option called external quantum efficiency. So you can plot the quantum efficiency characteristics as well. Similarly, whatever the type of structure you want to plot, you can plot according to your need. If you want to go for tandem one, this is called tandem structures, where P dot polymer ZNO interface P dot polymer aluminum. And here for the depth diffusion, we can run the simulation and let's see to run it. And you can plot the IV curve. This is current voltage characteristics from 0 volt to 1.5 volt. For display electrical characteristics, these are all electrical characteristics value. Now I want to go for LED application, basic one, and this one somehow you have got to know more details. You can also visit about this fluxim.com where some of the information are there. It is a licensed version tool which need to be purchased. If you want to see some more video for solar cell using the SETFOS, you can visit our channel. I would like to suggest you can type in your Google this channel Impulse Technology, innovate your research. We have a lot of video available, particularly in the same domain. Whatever you got our email related to that domain, these are all videos are available. Either solar cell, OLED, you can visit how this, either you are working on nanomaterial, you are working on solar cell, OLED. This is all videos are posted already available freely on our YouTube channel. So you can subscribe and like our channel to visit more. If you will go to the playlist, you can go to the SETFOS that is called SETFOS playlist. In that you can find these are some already video how for new different kind of solar cell and our OLED can be created. You can watch these video and you will automatically get to know how these things can be done in the SETFOS. Now I want to show you small things about LED as well because we have restriction of time. So I want to show you the LED basic idea. So for that I would like to click on file option and click on new option. So in this chapter I will take new simulation. So this new button, now default it is opened here. So for emissive property calculation, I have to enable the emission module. This is a bulb sign which will enable the emission module that I shown you in the PPT. The emission module is enabled that you can see here. The direction of the emission in SETFOS, it will calculate the emission spectra outcoupled through the top layer of the device structure. So we will calculate the emission into the glass substrate that we will create here. So we can also need to inverse the default stack as well. Now I want to add multiple layer in between surrounding and substrate. So I click on, I want to add 4 more layer in between the surrounding and substrate. Now the layer name, I have to define it from the top. So I want to define substrate. I want to define next layer is called ITO. Next layer I want to define that is called P dot. Next layer I want to define as a polymer. And then next layer I want to define as a calcium. And I can define as a aluminum. and this is called surrounding. This is my layer stack for LED. So I have to set the thickness of all layer. So let's suppose as an example, I want to set the thickness of all layer uh, to 10 nanometer. So the top layer and bottom layer are semi-infinite media, and the thickness is irrelevant for top and bottom layer. And the constant refractive index of each material will not show any dispersion. So I want to define the calcium real and imaginary part of the refractive index. Let's suppose as an example 0.75 and 2.2 for this calcium, and for this p dot layer I want to define n equal to 1.5. And this other layer I want to set the refractive index from my library. So I will click on import button and import ito.nk file. Similarly, for p dot layer, I can import from my library. And for this aluminum also, I want to import from my library. We can also edit the value, whatever given in the library. It can also become changed. If you want to change it, it can also be changed. And for polymer, I can take pfo.nk file for the polymer. Now it is added. Now all the refractive index for each layer has been added as a function of wavelength, and it is already displaying here as a function of wavelength. Refractive index has been added. It shows the real part on the left hand side and the imaginary part on the right hand side. Now the layer setting are completed. Next step is called the to set the emissive layer. So I want to set this polymer layer as a emissive layers. So you can see there is a emitter option is there. I can click on this emitter option and it will become emitter. To define the property of emitting dipole, this is emitting dipole luminescence option is there. I want to hide this layer structure for time being to visualize my structure properly. So I have to set the dipole distributions. Now you can see there is a luminance option is there. I will click on this luminance, there is PL data, photoluminance data is available in the library. You can see there is a AL alpha NPD, ALQ, ALQ3, BLQ, blue, PL data, green, IRPPY, super yellow, phosphor red, organic material, NEF data, all the organic material, this data is available. So I can import, let's suppose this MEHPPB organic material. I have imported this PL data. This is PL data, wavelength probability. And I have to enable this drifted diffusion module as well. One minute. Now each layer emitter and refractive index has been defined, and then I will go to this spectrum. So emission setting is there, where I can define the emission mode. Spectral, dissipation, power analysis, mode analysis options are there. So you can modify the wavelength also if you want to modify. I will check this layer as a transparent. Polymer layer as a transparent, I can activate. Now I want to run this OLED emissive property. Now you can see this is refracted color, emitted color, intrinsic color, visualized color are there. Accordingly, some property are calculated. Optical, electrical, EQE, Lambatian, CEIE color diagram, radiance, luminance, luminous efficiency, and other characteristics will also be plotted. Radiative dipole density, reflectance, absorptance, transmittance. This is emission spectrum, normalized emission, and white emissions. Now, if you want to perform the electrical calculation, then this module need to be enabled. Dip to diffusion, and you have to set the layer as electrode type. So this layer as electrode type, bottom one as electrode type. In between, you can set as a semiconducting. In between the electrode, you can set all layer become semiconductings. So once you will enable, there is this is single emitter layer. So multiple emitter layer, if you want to set, that will also become possible. Multiple emitter layer you can set. If you want to define the semiconducting property of these layers, so go to this and import from the library, or you can create by yourself. So for P dot layer, you can see there is a semiconducting material. And whatever polymer is there, you can take that polymer and you can also include it. I'm taking as an example. So once you will define the semiconducting material, and then you can also perform the sweeping option, that is called the sweeping option. And in the sweeping option, you can see you can also vary the emitter properties: position, lifetime, quantum efficiency, width, dipole, orientation, conversion, luminance spectrums, or not only single parameters, whatever parameter you want to sweep from minimum to maximum, single, one parameter, two parameter, three parameter, four parameter, multiple parameter you can sweep at a time. I want to take it from my library. I want to import from the database for one OLED example. Similar type need to be created. Now you can see this is single emitter layer where ITU, HTL, emission layer, ETL layer, it is there. And let it simulate this LED application. Now simulation is done. You can see this is emission property. And whatever other property you want to plot, you can see for emissive related property, CI color diagrams, luminous efficacy, and optoelectrical, optical electrical, current efficiency plot, luminance plot, radiance plot, and many more. Many more example is also given in the library. As you can see, these are the full OLED with three emitter layer, 1, 2, 3. And similarly, this is different other complex LED structure. It is given in the library. So people can also get it simulate, and then you will be able to plot it. Now I would like to unmute to all the participants' mic so that you can also ask your questions, and I can show the demo, rest of the demo according to your queries. So now participants, please unmute your mic and you can ask your questions so that I will show you whatever your questions are there. Thank you very much for listening and giving your time. Dear participant, kindly unmute your mic and you can ask your questions, please. I cannot hear. Dr. Arun Kumar, please. For the reference paper, you can visit on our website and you can find a lot of publication papers are there. Go to this research and publication option. Here you can find papers already available with their DOI numbers. Hello. Hello. So basically direct download option is not there. It is a license version tool which need to be purchased by your institute. So if anybody interested, you can keep contact to me. We can have a discussion and we can provide accordingly. Dear participant, do you have any questions? Please unmute your mic. So cost of the software depend on the module and number of years of validity. 1 module, 2 module, 3 module, 1 year, 3 year, 5 year, 10 year. So if you need it, kindly contact to us. We can have a discussion and we can provide you the quote. The minimum price you can assume around 2.5 to 3 lakhs. 2.5 to 3 lakh minimum pricing. It is starting for 2 module something. The license will be dongle based license where you can connect the dongle to your computer, any computer. It will not require high-end workstation, high-end server. Normal laptop can also run the job. You can connect the dongle to your system and you can run anywhere, anytime through the dongle. I think there is no questions. So I'm going to end of the sessions. If any questions are there in future, those who want to buy the software, there is an ongoing DST proposal scheme is going on for the state universities or private university, they can submit their regular faculty can submit the project on such software SETFOS to the government. Maybe government can help you to provide the funding to purchase this tool. So this is ongoing. It will be available, extended till 15th December. This call for proposal. So maybe some of the faculty can get the fund. If you want to discuss, you can let us know. Thank you very much from my side for giving the time to all the participants.